Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to continue our study of ordering of elements that we did in the last section. And we're going to talk about the topic of combinations. Okay, here's where things start to get a lot of students in trouble and the confusion begins to mount sometimes with some students. I hope to completely avoid it with you here, because the term permutation and ordering and combinations also has to do with elements and picking the different ways in which things can happen, the number of ways in which things can happen. It's easy to get confused, okay? The number one rule for permutations, which we just studied, was that the order does matter. The order of the elements matters. So I know you just watched that section. That's what that means, okay? When you're talking about combinations, the order doesn't matter. And that's why I tried to drill it home so much for you, is because when you're talking with combinations, the order does not matter, okay? The easiest way to probably get into that is just to go ahead and work an example and show you what I'm talking about of when the order might not matter at all. I mean, this is not rocket science. You're going to get this really quickly, and you'll look at the formula for how to calculate the number of combinations, and once you see the difference, you'll know when to apply the permutation rule and when to apply the combination rule. So let's go ahead and just briefly review what we did last section, because I'm going to draw some parallels to it, even though I know you just watched that section. Let's go ahead and talk about a race. Okay, we have three runners. I'm going to do this really quickly because you just watched the section. Three runners. How many ways can we get first and second place? First and second place. Now you know this is a problem in permutations from the last section, okay? And I'm going to show you the difference between this and a combination is why I'm doing this. This is a problem in permutations because there's a clear first and second place, and that's a big keyword that should tell you the order is going to matter. So if I had, for instance, Jake, Bill, and Sarah, what we did in the last section is we built our tree diagram, right? We said, well, Jake can finish first, and once we pick Jake, then Bill could finish second, or Sarah could finish second, okay? And we also said, okay, if Jake didn't finish first, let's say Bill finished first. Then Jake could finish second, and Sarah, in those cases, could finish second, okay? So this is first place, this is second place. And then if Sarah's actually the one to finish first, Jake could be the guy to finish second, and then Bill could be the guy to finish second. So this is just a review. We did this in the last section. I'm just showing you just for some comparison purposes. And then we said, okay, in the last section that when you have problems of this type, you have, in this case, three elements taken two at a time, okay? Taken two at a time. Because I had three elements, but I'm only looking at the number of ways in which two of them can be ordered where the order does matter, okay? And we said that was 3 factorial over 3 minus 2 factorial, okay? And when you do this, you'll get 3 factorial on the bottom and 1 factorial, 3 factorial on the top, 1 factorial on the bottom, and what you'll have is 3 factorial, which 3 times 2 is just going to give you 6. So there's 6 perms in that case. And this is exactly what you have. 1, 2, in this case, this would be 1 permutation, 2, 3, 4, 5, 6. There's 6 different ways in which you can have first and second place like that. So for this case, for this entire example, the order mattered. First place, second place, the order mattered. Now, let's move into the topic of this section, where we're not going to use the word permutation at all. It's not called a permutation. It's called a combination when the order does not matter, okay? So let's say we're going to use the same names to make it easily relatable. You have, what do we have here? We had Jake, Bill, and Sarah. Jake, Bill, and Sarah. But instead of winning a race where there's a clear first and second place winner, okay, let's say, for our problem, let's say we have 3 people, Jake, Bill, and Sarah, just like before, but we're going to send 2 of these 3 people to a conference in Colorado, let's say. And they're lucky winners of this thing, and there's not only enough money in the department at work to actually only send 2 of them. You can't send all 3 of them, okay? How many ways can we pick these people, okay? How many ways can we pick these people? Now, before I even write anything down, I want you to completely internalize the following thing, okay? It's different fundamentally from what I wrote on the board here, because here the order actually mattered quite a bit because it's a first place and a second place thing. But if I'm picking 2 people to go to a conference, okay, and let's say I pick Jake and Bill, let's say, to go to the conference. That's one ordering, right? One pairing. okay? If I pick Jake and Bill, and let's say vice president comes, out of the conference room and says, oh, let's pick Bill and Jake. Well, the one guy says, let's pick Jake and Bill. The other guy says, let's pick Bill and Jake. Well, they both look at each other and they say, well, that's the same two people. Okay, it doesn't really matter. Buy them plane tickets. Okay, the order actually didn't matter. There's no first place winner for the trip and second place winner for the trip. It's just two people are going. And Jake and Bill is exactly the same meaning as Bill and Jake for this particular problem because of the context of what it is. There's no difference in the ordering here, okay? It's not like you're picking a vice president and a president, and the order in which that this happens really matters, okay? You're picking two people, and as long as the same two names are in the list, it doesn't matter who's first and who's second. So obviously, there's going to be less combinations. Now they're called combinations when the order doesn't matter. There's going to be less combinations, okay? Because it doesn't really matter the order in which they're listed, okay? So if we were going to pick these people, and we have, by the way, Bill, Jake, and Sarah, okay? How could we do it? Well, we could pick Jake. Actually, let me go ahead. What I want to do now is switch colors because it'll make it a little bit easier, okay? We could pick Jake and Bill to go on the trip, okay? We could pick Jake and Sarah to go on the trip. And we could pick Bill and Sarah. Now, please take a second to make sure that you agree with this. The only three people we have to choose are Jake, Bill, and Sarah. Okay? So we can pick Jake and Bill. That's this ordering. This is one combination. Okay, it's not a permutation anymore because the order doesn't matter. It's a combination. Okay? Jake and Bill. We can also pick Jake and Sarah. That's another combination. Okay? But Jake and Bill is exactly the same thing as Bill and Jake. And Jake and Sarah is the exact same thing as Sarah and Jake for this one. And we can also pick Bill and Sarah and Bill are exactly the same thing. So if you try to go the other way and say, well, what about Bill and Jake? Well, that one's covered by this, even though they're in a different order. Well, what about Sarah and Jake? Well, that one's covered here. It's just in a different order. Well, what about Sarah and Bill? Well, that one's covered here. It's just this one's written down in a different order. But the order doesn't matter because we're just sending them on a plane trip somewhere. Okay? So what I'm getting at here is there's only three combinations. Three combinations, okay? So obviously, same three people, the context of this problem with the first place and the second place leads to 6 permutations. This problem, because there's really no first, second place, it's just pairings of people, unique pairings of people, okay? It's still 3 people taken 2 at a time, but it's not a permutation. It doesn't lead to as many different ways to do this thing because the order actually doesn't matter, okay? So the thing to take away from this problem is that anytime you have a problem, when you think about it, and you have to actually do think about it, and if you see that you have n elements taken r at a time, okay, but the order actually doesn't matter, then it's a problem in combinations. So mentally think about it and say, well, what if I flip the order of one of these pairings? Does it actually make a lick of difference? I mean, if it's a phone number, 8675309, I mean, if you change the numbers around, it's a different phone number, so that matters. But when you're talking about people sending to a conference, it doesn't matter the order, so it's a problem in combination. So you have to make that thing first and get that clear in your head, okay? So when you're doing a problem in combinations, you're going to use the following thing. The number of combinations of n elements taken r at, this is the lowercase r just like before, a time, is, now the only thing that's a little bit confusing, okay, is what you will usually see in your book is that the combination is usually going to be written like this, n and r, okay, with a parentheses. That's how it's usually going to be written in your book, most likely. This is just, you're just going to have to get used to this. There's no fraction here. It's not n divided by r. It's just n and r, and there's a parentheses here. Let me write it down, and we'll talk about it. What it is n factorial over n minus r factorial times r factorial. Okay? That's what it's equal to. Okay? Now, this is what you use when you have a problem in combinations. You have n elements taken r at a time, and you know it's a problem in combinations, you apply it. Here, you would look at this and you would say, I know it's a problem in combinations because the order doesn't matter. I have 3 people, I'm taking 2 at a time, and I'm trying to find out how many different combinations there are. So n would be 3, n would be 3, and r would be 2. So if you were going to do this the way you would write it on your paper for that particular problem, 3 and 2 would be 3 factorial over 3 minus 2 factorial, because this is n and this is r, times, again, 2 factorial. Okay, so what you would get on the top would be 3 factorial over 3 minus 1 is 1 factorial times 2 factorial. Okay, and so on the top you're going to have 3 times 2 times 1, and on the bottom you're going to have 1 factorial is 1 times 2 times 1. 2 factorial is 2 times 1. So you're going to have 2 on the bottom. So you're going to have 3 times 2 is 6 on the top, 2 on the bottom, and so the answer is going to be 3. 3 different combinations. And look, we just calculated there's 3 different combinations. There's 3 different ways to order these people to go off on their trip. Okay? So that's just kind of giving you a little bit of overview as to how to actually use the thing. It's pretty easy to use once you know to use it. It's just like everything else in life. I mean, it's always easy after you know the answer, right? I mean, it's the same thing here. The trick is, how do you know when to use it? How do you know when it's okay to use this instead of using the permutation formula? That comes with experience. Nobody's born with that, okay? So if you get confused reading a problem, don't throw the book across the room. It just takes practice. Go ahead and work a different problem until you get enough practice. Watch this section more than once if that's what it takes to get familiar with seeing problem after problem, and you'll get the hang of it. I mean, it's not that hard. You just have to give yourself some time. There's a couple of additional things I want to tell you about this thing. This thing you'll probably see in your book. I'm going to write it down for you just in case you do. This is really called a binomial coefficient. Okay. The only reason I'm even telling you that is because you'll probably see it in your book, and it has a big fancy word called binomial coefficient. What's going on here is, if you remember back to your college algebra or your advanced algebra or whatever class you took where you learned about algebra, beyond the basics of algebra, you may or may not, you probably did, hopefully, learn about something called a binomial expansion. And the binomial expansion is just a way to simplify some algebra in certain ways and to expand algebraic expressions, okay? And if you were to dust the rust off of your brain, if you ever learn that, go back and look at that section in your algebra book. The binomial expansion is going to tell you how to expand certain algebraic expressions. And it turns out that the coefficients of the expansion, okay, that you do are called binomial coefficients. And the binomial coefficients is exactly defined as that right there, okay? So it turns out that the same coefficients that have some value in algebra to expand equations, to expand expressions of certain types, is very useful in probability. That's all. So it's exactly the same thing, and that's why they use this parentheses notation here, because this is how it's written when you're talking about binomial expansion, binomial coefficients way back in algebra. So this is a good example of some branch of math that actually applies to probability and also to algebra. So you may have heard this, binomial coefficient. If you haven't, it doesn't really matter. I'm just telling you that just so you'll know that's where it comes from, and also because your book probably will mention it as well. Okay. The other thing I want to mention to you is just turn your attention back over here when we're looking at the permutations. The formula for the permutation was n factorial over n minus r factorial. Compare these two things here. N factorial over n minus r factorial. The only difference here is that for the combination, the only difference between this and the permutation formula is you're dividing by an extra r factorial. This whole unit right here is equal to the permutation, this whole thing right here. And so if you divide that by r factorial, that's what this is, okay? So really what you're doing when you're doing the combinations, I mean, going back over here, you have the same 3 people, you're looking at 2 at a time, but when it's a permutation, the order does matter. So you get a bigger number. Whenever you're looking at the equivalent problem in combinations, 3 people taken 2 at a time, but the order doesn't matter, you only get 3 people. So you get less people okay, whenever you look at the combinations, because the order doesn't matter. You're going to have less different valid ways to order the things, okay? So the combination formula makes sense that it's really going to be equal to the permutations divided by something. And this something is, I'm not going to prove it to you why it's this way. I'm just presenting this as a fact and you'll have to use it. I'm just saying it makes sense. You take the number of permutations, you divide by a number, r factorial, and it makes the number of combinations smaller, which makes sense. The number of combinations should always be smaller than the equivalent problem if it were a permutation problem, because in the combinations the order doesn't matter, okay? So let's go ahead and work a bunch of problems here, and by working the problems and seeing how they're phrased and worded, I want you to really focus on getting the hang of identifying when the problem is a problem in combinations versus permutations that we did before. Once you get that licked, the rest of it isn't hard. The math is not very hard. In general, that's the good thing about the probability class in general, the entire course. The math really isn't that hard. The challenge is figuring out what to do. Usually once you figure out what to do, the math is like 2 lines of multiplication. It's not a big deal. The trick is knowing what to do, and that's the challenge. Okay, the first problem says on an election ballot, you select 3 officials from a group of 6 candidates. How many ways can you do this? Okay, so when you first read these problems, I mean, it's crucial that you really figure out, is it a problem in permutations or is it a problem in combinations? You've just done a whole bunch of problems in permutations in the last section. These problems are all going to have a slightly different flavor. It's up to you, by doing these things and working with me, to be able to identify for yourself when it's a problem in combinations, okay? The first thing you notice is there's no first, second, or third place here. There's no vice president, president. There's nothing specific, okay? There's nothing specific telling you that the different ordering is going to matter at all. It's just that there's an election and there's 6 people running for office, but for whatever reason, I'm picking only 3 of them, okay? Maybe I'm taking a survey with my friends. Maybe we have 6 candidates and I put them all on the wall and I ask a bunch of my friends, hey, who do you think are the 3 best candidates on this list? We're not asking about vice president, president, and treasurer. We're just saying, who do you think are the best 3 people? Well, the order isn't going to matter. If somebody says Tom, Dick, and Harry, and the other person says Harry, Dick, and Tom, those are the same 3 people. So the order doesn't matter. So the problem says you select 3 officials from a group of 6. Okay? How many ways can you do this? It doesn't say anything about the order of vice president or president or anything like that. It's very general. The order doesn't matter for this problem. Okay? So now that you know that, the order does not matter, so it's a problem in combinations. The general form for the problem in combinations is n factorial over n minus r factorial times r factorial. Okay? And in this problem, n is equal to 6 because I have 6 people running for office and I'm taking them 3 at a time because I'm taking 3. It says 6 people and I select 3. So n is 6 and r is 3. So all you do is put it in here. And you can see the math isn't that big of a deal once you know what numbers to put in here. So 6 minus 3, because n and r factorial, times 3 factorial. By the way, I'll give you a rule of thumb, okay? Try not to skip too many steps when you're plugging numbers in here. It's very tempting to look at n minus r and just do the subtraction and try to skip steps. I mean, that doesn't do anybody any favors. Use the paper. If you try to skip too many steps at once, you're probably just going to make a mistake. Okay, so on the top you have 6 factorial. On the bottom, 6 minus 3 is 3 factorial. Again, times 3 factorial from here. And you could bang this out in your calculator. 6 factorial you could multiply, and you can multiply this on the bottom. But really what you're doing is on the top you have 6 times 5 times 4 times 2 times 1. On the bottom, this 3 factorial is 3 times 2 times 1. This factorial over here is again 3 times 2 times 1. So what you notice, and the reason I'm writing it out, is because these factorials are going to, these multiplications are going to cancel with those. So really what you have in the end is 6 times 5 times 4 on the top, and on the bottom 3 times 2 times 1. So on the top you have 120, 6 times 5 times 4, and on the bottom you have 3 times 2 is 6. So what you have is, when you divide these out, 20 ways. And you don't say that they're permutations because here the order didn't matter. You say that they're combinations. So it's very important for you to understand the difference between this problem, because for the permutation problems you'll have an n and an r, and for the combination problems you'll have an n and an r. And if you don't know what you're looking for, you won't know what to do with these numbers. So you need to make sure you understand that because this problem didn't have any specific orderings, and it was just sort of a general, how can how many ways can you pick these people kind of thing, it's a problem in combinations. And once you know that, it gets a little bit easier, okay? Now the next problem says, it's a little bit more challenging, but it's, again, not too bad. To win the lottery, you must pick 6 numbers from 49 balls. 6 numbers from 49 balls. The order that you pick the numbers does not matter. How many selections are possible? Okay? So what it's saying is, let's read it one more time. You have a lottery here. You know from your experience that it's very improbable to win the lottery. There's a lot of different combinations of balls. Otherwise, it'd be really easy to win, right? So you expect a very large number. So let's see what we get. You have 6 numbers out of 49 balls, okay? So really what this is saying is you have 49 elements and you're taking 6 at a time. So you have, imagine 49 little balls in front, but I can only pick 6 at a time. I can pick this 6, I can pick this 6, I can take 2 from over here and 4 from over there, and 3 from over here and 3 from over there. I can pick them in all different combinations, and that's why there's so many different ways, for you to lose with the lottery, really. Okay, first question, is it a problem in permutations or combinations? Okay, well, when you think about it, you have 49 balls and I'm picking 6 of them. I haven't said anything about specific ordering of anything. In fact, it says the order you pick the balls doesn't matter. Okay, the easiest way to figure out if it's a problem in permutations or combinations is just mentally think. If I take one of the answers and flip one of the numbers, does it actually change? Does it qualify for a new ordering? Now let's go ahead and see if that's true. Okay, we have 6 balls. Let's say you pick, just for grins here. Let's say you pick 1, 2, 3, 4, 5, 6. Those are your lottery numbers. Okay, and then let's say your dad buys a lottery ticket and he buys 6, 5, 4, 3, 2, 1. My question is, are those the same 2 lottery tickets? I mean, if I present this ticket to the lottery commissioner, and this is actually what balls come out, I win. And if I present this ticket to the lottery commissioner, I'm still going to win because the order doesn't matter in this answer. Okay, it doesn't matter at all. It just matters what balls you pick. So the order does not matter in this problem. So it's not a problem in permutations. It's a problem in combinations. That's crucial. So just try to flip some of the numbers around, in whatever problem you're working, and see if it makes a difference. And if it doesn't, then it's combinations. Okay. So the number of balls is 49, so I have 49 elements, and I'm taking them 6 at a time. So R is 6. So the number of combinations is n factorial, n minus r factorial times r factorial. Okay? N factorial over n minus r factorial times r factorial. All right, so let's go ahead and plug it in there and see what we get. N is 49. Factorial. On the bottom, you'll have 49 minus 6 factorial, 49 minus 6 times 6 factorial. Okay? So over here, what you're going to have is 49 factorial times, what's 49 minus 6 is going to be 43 factorial times 6 factorial. Now, you should know or think that these factorial numbers are going to be huge. If you put 49 factorial in your calculator, that's 49 times 48 times 47 all the way down to 1. It's going to be a very, 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 very big number, okay? So rather than try to do that calculation, let's just go ahead and think about what this means. 49 on the top times 48 times 47 times 46 times ... all the way down to 1. And on the bottom, what you're going to have, 43, you're going to have 43 times 42 times 41 times ... all the way to 1. Okay, and this is again going to be multiplied by 6 factorial, so I'm going to have 6 factorial. I'm just going to leave that there. The reason I'm doing it is because I'm telling you that you can I can't really write it all out to really show you, but because you have 49 multiplied down, everything from 43 on is going to cancel with what's on the top because everything's multiplied together. So what you're going to have, if you were to write all this down, on the top you'd have 49 times 48 times 47 times 46 times 45 times 44. Everything below that, 43 and below, cancels with all of these 43s and below. And on the bottom, you're going to have 6 times 5 times 4 times 3 times 2 times 1. That's what's going on here. Okay? And if you were to take 49 times 48 and on down to 44 and then divide it by this, on the top, you'll get a very, very large number. You'll have 1, 0, 0, 6, 8, 3, 4, 7, 5, 2, 0. And on the bottom, 6 factorial is just going to be 720. And when you divide those two numbers together, you will get 139,83816. Okay? 13,983,816 combinations. It's not a permutation because the order actually doesn't matter at all that you pick the balls. Think about that. 13,983,816. Okay? Those are the different ways in which you can choose the balls. There's a lot of combinations there. So the first step is to go in and see if the order matters. In this case, the order doesn't matter because if you change the order in the balls that you pick or if somebody else has a different lottery ticket with the same numbers in a different order, it doesn't matter at all. So it's a problem in combinations. You have n elements, 49 elements taken 6 at a time. That's the number of ways in which you can choose those numbers. Okay, the next problem says, how many ways can a manufacturer choose 2 warehouses from 20 choices? Okay, how many ways can a manufacturer choose 2 warehouses from 20 choices? So you have 20 choices laid out in front of you. Some are on 1st Street, some are on 2nd Street, some are on, Palm Avenue. They're on different places in the city, okay? And I'm going to choose 2 of them, okay? Now this problem, you have to ask yourself, is it permutation or is it a combination? This problem has nothing to do with order. There's no first place, second place. There's no specific ordering involved. If my vice president of marketing decides to pick the warehouse on Palm Street and Poplar Street, okay, and then somebody else in the office says, well, why don't we pick the one on Poplar Street and Palm Street? Well, it's the same warehouses, just in a different order. Well, you see, that means the order doesn't matter at all, okay? It doesn't matter if you choose the one on Palm Street first or Poplar Street first, but as long as those 2 things are ordered and paired together, that is a valid choice. And flipping the order of the 2 warehouses that you pick doesn't affect anything. So it's a problem in combinations, okay? Once you know it's a problem in combinations, the order doesn't matter. It's a simple matter of just calculating the answer, okay? So the formula for combination is n factorial over n minus r factorial times r factorial, okay? N was the fact that I had 20 warehouses, and R was the fact that I was taking 2 of them. N choices, N elements taken 2 at a time. That's what I'm doing here. So that's why N is 20 and R is 2. So it's 20 and 2. So it's 20 factorial over 20 minus 2 factorial times 2 factorial. Okay? So what I'm going to have here is 20 factorial over 20 minus 2 is 18 factorial times 2 factorial. Okay? And again, I can do all this multiplication, that's fine, but what you'll find out here basically is I have 20 times 19 times 18 times 17 all the way down. 18 factorial is 18 times 17 times 16 and on down. So because you're going to have all these cancellations, what you're going to have is 20 times 19 on the top, and you're going to have 2 times 1 for the 2 factorial on the bottom. Everything below 19 up here in the top, which is times 18 times 17, 16, 15, 14, all that is going to cancel with the 18 factorial, which is, again, 18 times 17 times 16. All those are going to cancel just like in the previous problems. So really what you have here is 20 times 19 over 2, effectively, is what you're going to actually have here. Okay? So when you do that, you can just sort of do that math there, and what you'll find is that you'll have 190 ways, which are called combinations. Not permutations. They're called combinations because the order actually didn't matter at all, okay? The order actually didn't matter at all, okay? And the final problem that we're going to do, just to kind of illustrate the difference between permutations and combinations, is a little bit more tricky, but not so tricky really when you think about it. A manufacturer has 8 motors and 5 switches, okay? And how many ways can you select 2 motors and 2 switches to build a project, okay? This is a little bit different than what we've had before. It's not quite so cookie cutter, but let me walk you through it and show you why it's the way it is. The first thing to think about is this a problem in permutations or combinations? Okay? Does the order matter? Okay? You have 8 motors and 5 switches. How many ways can you pick 2 motors and 2 switches? Well, this has nothing to do with a first place or a second place or a specific ordering. I mean, if I've got 8 motors out in front of me and my employee picks, motor A and motor B, and then some other employee picks motor B and then motor A, I mean, that doesn't matter. I'm picking 2 motors at a time. It doesn't matter the order in which I pick the motors. That's not what I'm talking about here. There's no race involved. There's no specific ordering like that. So it's a problem in combinations. The only thing that makes this problem a little bit trickier is that you have 8 motors and 5 switches, but I'm picking 2 motors and 2 switches. How do I do that? Well, let's walk through it one step at a time. Since we know we're picking 2 motors, okay, and we know we're picking 2 switches, let's first find the number of combinations, the number of ways that I can pick 2 motors from a pool of 8 motors. Let's do that first and find out what that comes out to. So what I'm going to have here is I have 8 motors and I'm going to select 2 of them. So this 8 motors taken 2 at a time. So what I'm going to have, because we know it's a problem in combinations, is going to be 8 over 2. It's n factorial over n minus r factorial times r factorial. That's what it is. N is 8, r is 2. So it's 8 factorial over 8 minus 2 factorial times 2 factorial. Okay? And what we're going to have here is, on the top, 8 factorial over 8 minus 2 is 6. 6 factorial times 2 factorial. Okay? So on the top, again, you're going to have your 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And on the bottom, 6 factorial, you have your 6 times 5 times 4 times 3 times 2 times 1. And then you still have your 2 factorial, so 2 times 1. Now, the reason I wrote it out, really, I didn't have to write all of it out, but the 6, 5, 4, 3, 2, 1 is going to cancel with the 6, 5, 4, 3, 2, 1. Okay? So really what you're going to be left with is 8 times 7 over 2 times 1 is going to give you 2. So really what you have here is 8 times 7 is 56 over 2, which is 28 ways or combinations. 28 combinations. What does this mean? 28 ways of picking 2 motors out of a pool of 8, where the order doesn't matter because I'm not picking any in a specific order. Now, the problem said I had 8 motors and 5 switches. I'm taking 2 motors and 2 switches. How many ways can I do that? Well, all I've done here is I found that there's 28 ways to pick the motors. That's all I figured out. Now let's do the same thing for the switches. For the switches, I have 5 switches. Select 2 at a time. Okay, so it's going to be the same story. 5 switches taken 2 at a time. Let's see how many ways we can do that. Okay, so you're going to have n factorial over n minus r factorial times r factorial. And so n is 5 and r is 2. So you'll have 5 factorial over 5 minus 2 factorial times 2 factorial. Okay. So on the top, you'll have 5 factorial over 5 minus 2 is 3 factorial, and then here you'll still have your 2 factorial. Okay? So really all you're going to have is 5 times 4 times 3 times 2 times 1, and on the bottom, 3 factorial is 3 times 2 times 1 times 2 factorial, 2 times 1. Okay? So really all you're going to have is 3 cancels with 2, cancels with 1. So on the top, you're going to have 5 times 4 over 2 times 1 gives you 2. 5 times 4 is going to give me 20 over 2. So it's going to be 10 ways or combinations. Okay, so let's review what we've done. Okay, the problem says we have to pick 2 motors and 2 switches of a pool of 8 motors and 5 switches. Okay, so we found out that there's 28 ways to actually pick the motors to get 2 of them, and there's actually 10 ways to get 2 switches. There's 10 different ways to do that. Okay, so here's where the fundamental thing comes into place. What do you do with these numbers? Okay, I mean the answer is how many ways can you do all this stuff together? Well, you can kind of think as event number 1 being the act of selecting 2 motors, and you can kind of think as event number 2 as the act of selecting the 2 motors. So event 1 can actually happen 28 ways, the act of taking 2 motors. And event number 2 can actually happen 10 ways, the act of picking the 2 switches. Okay? So because this is kind of like the fundamental counting principle here. Event 1, picking the 2 motors, happens 28 ways. Event 2, which is the number of ways you can pick the switches, happens 10 ways. So altogether, when you have all of these things going on at once, you can select the motors in 28 ways and the switches in 10 ways. There's actually a grand total of 280 ways to do the whole thing, which are combinations. Okay, and that's a leap of faith you'll just have to sort of take and just make sure you understand. I hope I've explained it right, and it's not the thing that would really jump out at you, but when you have a problem like this, if you know it's a problem in combinations, find the combinations of one part of the problem, find the combinations in the other part of the problem, and when you think of it in terms of the fundamental counting principle, this is event 1, picking the motors. Event 2 is picking the 2 switches. Multiplying them together using the fundamental counting principle gives me the total number of ways in which the whole thing can happen, okay? So that's what we're doing here, because I can do the first thing 28 ways and the second thing 10 ways. Multiplying them together multiplies the different ways that everything can be done, okay? So in this section, I've tried to outline the main differences between what a combination is as opposed to a permutation. Permutation in the last section was when you have n elements and you're taking them r at a time, and you're looking at the different ways in which you can choose those elements when the order matters. Usually it's a race, or it's a presidential election, or something where the order actually matters. Or it's a phone number. We did lots of problems with phone numbers and things like that in the other section, where you change the order of the numbers and it's a different phone number, okay? But in every problem in this section with combinations, the order didn't matter at all. When you look back, you'll see that every problem, you had the same n elements taken r at a time, but in every one of these problems, if you change the order, it actually, based on the word problem itself, it didn't actually change the fact that it was a valid pairing. So the order actually didn't matter. That's why in this class it's so incredibly important for you to read the problems carefully, figure out if it's a permutation or a combination, and then go accordingly, because in both of these problems you'll have an n and an r, and you really need to know where to apply it. So reading the problems and practicing problems is the only way to get good at them. And that is a good primer in how to solve problems in combinations.